Okay. And now let me give David the right to speak. What name is listed in the participant list for you? Sorry, you're on top of the list because you're sharing. That's why I didn't find you where I was looking. Okay, so we should hear you now.
Can everyone hear me?
Yes, we can hear you. Okay, so sorry for the small delay, and welcome to the next session, which is about concurrency and any kind of self-star algorithms and even more. And the first talk is going to be about recoverable mutual exclusion, and David is going to give the talk. Please go.
Okay, so this paper is by me and Philip from the University of Calgary. And we were actually working on the same problem as the best student paper. So I will be skipping a lot of things that is repeated. So the main thing to know about the recoverable mutual exclusion problem is just that processes can clash and then they are required to return back to the cycle. In addition, that means that if a process clashes inside the critical section, then the critical section must be reserved for this process until it comes back. Nobody else can enter it. Now, this little work has been gone over before, so I'll skip to the part that we are interested in, which is the work that goes beyond the log n over log n lower bound that we commonly see. And so the best student paper had one such result. They showed that when there are only f recent clashes, then you can bring the IMR complexity down to 1 plus square root of f. And there are two other papers that achieve better worst case lower bound, but these papers use non-standard primitives that are not implemented in common hardware architectures. So in this paper, we have another algorithm that is O1, but amortized. And to achieve this, we use the primitive fetch and increment. So the core of this algorithm will be two fetch and increment objects. The first is a fetch and increment we call C, and this just stores the number of attempts that have been started. So at the start of the enter protocol, the processes would just try to increment this C, and then they will order themselves according to the value that they receive. So this effectively creates a queue of the processes. And in a world that have no clashes, this would be enough. However, when there are clashes, this can result in holes in the queue. So if a process comes and increments C, and then he immediately clashes without telling anybody what value he got, then nobody can ever find out who was in that position of the queue. So to get around this problem, we have another fetch and increment D. And this records the number of attempts that have either completed or failed. So whenever a process joins the queue, it would increment D. And whenever a process clashes, it would increment D when it recovers. Now, the rest of the processes, whenever they see a hole in the queue, they would look at the values in C and D. And if the value in C is at most the value in D, that indicates that some processes have failed and the hole may never be filled. So let's skip the hole and move on. And this is, in fact, where the amortized IMR complexity comes from, because if there are many processes that clash, they could force the other processes to do a lot of work to skip over their attempts. So in conclusion, we have an IME algorithm with constant amortized IMR complexity, cast and fetch and increment primitives, but it uses unbounded space, and it only achieves a weak version of the very desirable starvation freedom property. So naturally, we have a bunch of open questions, such as the most important one is, we have a constant amortized IMR complexity, but is there an algorithm with constant worst case IMR complexity? And for this, we don't know. On the other hand, we have some improvements to this algorithm, which we believe will bound the space and achieve strong starvation freedom. And that's the end of the talk.
Okay, thank you very much. So are there any questions? Are there maybe any questions on Zulip already? If none are in the Zoom chat right now. No questions? I'll assume that the talk was very clear then, and any follow-up questions can be taken offline. Thank you. So the next speaker can bring up the screen. All right, so we move on to the next talk, which is about population protocols for majority with a limited number of states. And this will be presented by Martin Kraus. Apologies if I don't get the name right. And now let me get your audio on, and there you go.
Thank you. So I'm Martin Kraus. I'm going to speak about the majority problem in population protocols. This is a joint work with Stav Ben-Nun, Zvi Kopelowitz, and Eli Porat. So in the population protocol, we have n agents or nodes that have pairwise interactions by a random and uniform scheduler. So on each round, two nodes are selected randomly, and then they can observe each other's state and update their own state according to some transition function. In the majority problem, each node has an initial color, which is black or white, and we want all the nodes to know what was the initial majority color. So in this example, we want all the nodes to report black as that was the initial majority color. Efficiency here is measured by the number of interactions until a stabilization, which means until all the nodes know what was the majority initial color. This can be mounted, of course, only with high probability and in expectation, since on each round, the two nodes are selected randomly. And also we want a small number of states per node. Typically we want a polylogarithmic number of states per node. So the framework that most protocols use, and also we use that framework, is the cancellation duplications framework. So we have log n phases to the protocol. And on each phase, we have two stages, as you can see in the illustration. There is a cancellation stage where blue and black nodes interact and cancel each other into empty color nodes. After a cancellation stage, most of the nodes are empty. And there is a duplication stage where every colored node that left in the population duplicates itself once into an empty color node, as you can see in the illustration as well. So after the whole phase, the difference between the majority and the minority colors doubles. Therefore, of course, after at most log n phases, there will be no more minority color nodes in the population. This works only as long as each node interacts theta of log n times per phase. However, Berenbeck et al. Recently proposed shorter phases of only theta of log to the 1 minus a n interactions per node. Of course, now that the phases are shorter, there is not enough time or not enough interactions per node, so we can guarantee that all the nodes duplicate in a phase. Some of them might not duplicate. So the solution is to notice that if not all the nodes duplicate, if there is still a small amount of nodes that don't duplicate, we are still fine. We're doing so by they do so by adding a catch-up phase. So as you can see here, there are some short regular phases of cancellation and duplication, and after some short regular phases, we had a catch-up phase. In the catch-up phase, a node that didn't manage to participate in the duplication, we call it an out-of-sync node. An out-of-sync node can duplicate sufficiently in the catch-up phase. So as we said, we want only a few number of nodes to not participate in the duplication during a phase. How many such nodes there are? So Bernberg et al. Bounded the number of nodes in this expression. The first term is nodes that didn't participate in the duplication due to the short phase reason, which means they didn't find any empty color node to duplicate into. We will not discuss this term. We will discuss the second reason, the deviation reason. Since each node knows its phase, knows in which phase it is by a counter, a node's counter can be far away from the average counter. So when most of the nodes are in, let's say, phase I, this node is in some other phase J, and most of its interactions are meaningless. We change the 1 minus 2a in the exponent to 1 minus a by tighten the curve. So most of the nodes are together in each phase. How do we do so? We are using the power of two choices. So the counter, instead of the counter that you see here, that increments both of the nodes, we increment only one of the nodes, only the node with the smaller counter. By doing so, by increment only the node with the smaller counter, we use a proof by Bernberg et al. From stock 2000 that says that the number of nodes that the counter is far away from the average, which means at least omega of log to the 1 minus an, at least a phase away from the average, is the desired expression. It's only n over 2 to the theta of log to the 1 minus a m nodes, with high probability, of course. And therefore, we can prove that the expected number of duplications in the catch-up phase is at most, with high probability, the log expression, which is explained in the paper. And this expression is little o of n when a is at most when a is at most half. So we set a to be 1/2. And Bernberg et al. Proved that if the number of out-of-sync nodes of duplications in the catch-up phase is at most little o of n, then with high probability all the duplications will sufficiently happen. So to conclude, we have an O of log n phases protocol, which means only O of n to the log to the 3/2 n log to the 3/2 n interactions for the protocol. And also we have log n states per node by some tricks of Altar et al. Thank you very much. If there are any questions, I'd be happy to answer.
Okay, thanks for the talk. I don't see any questions yet, but I have one myself. Do you have any reason to believe that log to the 3/2n is kind of the right answer, or do you think it's just a matter of getting better techniques?
We believe it's not, and we do try to improve it. But
so you expect a logarithmic complexity in terms
hopefully, not easily.
Do we have any other questions? Don't be shy. Okay, so if there are no other questions, then thanks again, and let's move on to the next talk. So the next speaker can, yes. And now let me give you the right to speak. So you, yes, we should be able to hear you now. Can you say something?
Hello, everyone.
Yes, hello. Okay, so the next talk is about multi-writer atomic registers, and they are to be implemented in a distributed fashion. And Kyle is giving the talk. Apologies if I mispronounce. Please go ahead.
Hello, everyone. In this talk, I will present our work on fine-grained analysis on first implementations of distributed multi-write atomic registers. I'm Kyle Huang from Nanjing University, China. Data replication is widely used in distributed storage systems. When programming over distributed data replicas, the consistency model acts as the contract between the developers and the distributed systems. Atomicity is a widely used strong consistency model. It allows concurrent processes to access logically the same data as if they were accessing one data item in a sequential manner. When programming over distributed data replicas, current systems are widely used to model the interaction between the clients and the data replicas. In current systems, the data access latency is mainly decided by the number of round trips of communications. For all possible implementations, we have the simpler single write case as well as the more complex multi-write case. We use W2, R2 to denote the implementations, which imply 2 round trips of both read and write operations. One round trip is obviously optimal to guarantee atomicity. So when either a read or write operation implies one single round trip, it is called a fast read or write. The famous AVD algorithm and its extension show us that 2 round trips are sufficient to guarantee atomicity. As for fast implementations, in the single writer case, the impossibility proof and the algorithm design are proposed. In the multi-writer case, it is proved impossible to maintain atomicity when both read and write operations are required to be fast. When we examine all possible fast implementations in a finer granularity, it is still open that whether it is possible to maintain atomicity when only either read or write is required to be fast, where the other operation can have 2 round trips. Towards solving these 2 open problems, the impossibility result can be obtained when we restrict the implementation to be semi-fast, or when we change the model of computation to the 1.5 round trip model. However, the core problems still remain open when we allow any fast read or fast write implementations. And we solve the 2 remaining open problems in this work. Our main contribution presented in this talk is the impossibility proof for fast write implementation. To derive the impossibility proof for fast write implementations, we are faced with 2 critical challenges. First, the read operation can now imply 2 round trips, so it has more power to break the indistinguishability constructed in the traditional chain argument. Second, the first round trip of a read operation can possibly affect what other clients may read. To address the first challenge, we use a 3-phase chain argument. In the first phase, we swap 2 write operations on every server and get the chain alpha. In the second phase, we append 2 read operations. We swap the 2 second round trips on every server and get the chain beta. Read operations in the head and tail executions of chain beta return different values. In phase 3, We construct the indistinguishability between beta 0 and beta s through a relaying execution chain gamma, and this will lead to contradiction and give us the impossibility proof. To address this second challenge, we eliminate all the servers which are affected by the first round trip. Since in the first round trip, the client does not know anything about the outside world, it can only blindly update the data on the servers. Our chain argument can still be conducted on the remaining servers. In summary, we analyze fast implementations of atomic registers in a finer granularity. For fast write implementations, we give an impossibility proof. For fast read implementations, we also give the impossibility proof and the algorithm design. This is the end of my presentation. Thank you.
Thank you very much. Again, I don't see any immediate questions, so if you have any, please post them. A question I have, so do you have an educated guess, or have you even tried out in some way whether this can make things faster in practice?
A good question. Let me see. I think sorry. It's a little.
I mean, I'm not expecting that you can answer this right on the spot if you haven't thought about it before. That's okay.
Sorry.
Do you have any other questions? Okay, that doesn't seem to be the case. Then thanks again. And the next speaker, please bring up your screen. And you should be unmuted now.
Okay. Hi.
Hi, yes, we can hear you. So
okay.
The next talk is going to be about self-stabilizing version of leader election in regular graphs. So we come to the self-star portion of the session. And
Okay.
Ho-Lin is giving the talk. Please go ahead.
Okay. Thank you for the intro. Today I'll be talking about self-stabilizing leader election in regular graphs. My name is Ho-Lin Chen, and this is a joint work with my student Xue and we're from National Taiwan University. So our work focuses on population protocols, in which we have a large number of identical and anonymous agents, and they can only perform pairwise interactions. So the problem we are trying to solve is leader election. So given the initial configuration, we want the system to eventually reach a safe configuration with exactly one leader. And then we want the system to keep this unique leader forever, meaning that this particular leader agent should stay in the leader state forever, and no other leader should ever be generated. Most of the previous works on leader election assumes that all agents start with the same initial states. And there were a lot of related works, including the brief announcement talk right after my talk. In our work, we focus on a slightly different problem called self-stabilizing leader election, or SSLE for short, in which we assume that the agents can start with arbitrary states. So initially, there could be no leader, there could be multiple leaders, but regardless of the initial configuration, we still want to reach a safe configuration with a unique leader at some point. However, if we allow every pair of agents to talk to each other, we already know that this is not possible without extra information. So instead, we focus on population protocols with special communication graphs. So here we have an underlying communication graph structure where every node is an agent and every agent can only talk to its neighbors, but they are still anonymous and they have no idea about the graph structure. So it's pretty much the same, except that only neighboring pairs of agents can react. All of the previous self-stabilizing leader election works basically focus on directed rings. So previously, there were protocols which worked on rings of arbitrary sizes and only uses a constant number of states. So we have extended the previous work to an SSLE protocol on arbitrary k-regular graphs. So again, our protocol is a single protocol that works for all graphs of the same degree, regardless of the size of graph. And the state required for each agent is also independent of the graph size. So it only depends, the number of states required is only depends on the degree of the node. We have two different constructions. The first one, the virtual ring protocol, is more intuitive and simpler, but requires an exponential number of states. And the second one, the spanning tree protocol, is more complicated, but only requires a polynomial number of states. So let me briefly describe these two things. So in the first one, the virtual ring protocol, we basically divide every agent into basically k virtual agents. Each one has degree 2. And if we do that, the graph is essentially decomposed into a collection of rings. And then we rely on the previous SSLE protocol on each of the rings. So we can elect one leader on each of these rings. And then this leader can send out signals to kill each other. So if there are more than one leader, then they will detect each other and essentially reset the graph. So eventually, when the system stabilizes, there's only one leader and one signal in the whole system. Therefore, completes our leader election protocol. On the other hand, for the spanning tree protocol, in order to reduce the number of states, now we cannot use a large number of virtual nodes for each node. So instead, we ask each node to randomly select a parent. And so we hope that the graph is going to go into a spanning tree where we can assign the root to be the leader. And of course, there could be 0 leaders where there will be a cycle. And in that case, we can use the previous leader election problem on leader election protocol on cycles to elect the leader and break this cycle. In the second case, there could be multiple leaders. In this case, there will be multiple roots and they can send out signals. And these signals, we can design them to traverse through each tree in a clever way so that the signals can always meet each other and reset the whole system. Okay, so when there are no leaders, the previous leader election system can elect the leader on the ring, therefore solve the problem. And so that's basically all I'm going to talk about today. So as a summary, we have 2 leader election protocols. Both works on arbitrary size k-regular graphs. Thank you for your attention. I'm happy to take any questions.
Thank you for this talk. This time there's an immediate question. So the question is whether what is the stabilization time, or do you have any bounds on the stabilization time?
Okay, so the time is really bad. So the previous work on the ring protocol is e to the order of n squared. And we use that as a sub-protocol. So we use we are adding at least one more exponent. So it's at least doubly exponential, at least 2 to the 2 to the order of n squared. Probably much more than that.
Okay, thanks. So Andrea also has a question. You posted it in the chat, so I will just read it out. So the question is, given the underlying topology assumption, this algorithm actually works for any graph where nodes are activated in a uniform manner, correct?
Actually, as long as the reaction sequence satisfies global fairness, our protocol will eventually work.
Okay, the next one is from Eric Severson. K is hard-coded for both of these protocols, right? do you
Yes,
think it
yes,
would be
case.
possible to extend these ideas to work with just an upper bound on the degree of each node?
We cannot allow classes of graphs that contains itself. So so for that, I think it directly implies an impossibility result if we only know an upper bound on K. So we must know what exactly K is.
Okay, so quick question from myself. So when you started talking about the spanning tree, I was immediately wondering how works on self-stabilizing spanning trees relate. So the key thing here seems to be that because you have the option to deal with the cycle, you don't actually need to keep track of the depth of nodes in the trees, and that allows you to keep the number of states small. Is that correct?
Right, right, that's correct.
Okay. All right, so if there are no more questions, then I would like to thank you again.
Thank you.
And please, the next speaker can bring up the screen. Okay. So we should be able to hear you now.
Okay. Can you hear me?
Yes, yes.
Okay.
So the next talk is a brief announcement, and it's also about leader election, but this time in population protocols. And George is going to give the talk. Please go ahead.
Thank you. This is joint work with Petra Bernbrink and Peter Klinke. Quick reminder of the model and the problem. So we have n agents, which are identical finite state automata. In each step of the protocol, a random pair of agents interact with each other. And in the leader election problem, we assume that all agents start from the same initial state. And eventually, the goal is that we reach a configuration where exactly one agent is in a leader state. And this remains true thereafter. The parallel stabilization time is the number of interactions divided by n, and this together with the number of states is the main complexity measures of interest. A large volume of work has been devoted to this problem, including both algorithms and lower bounds, and our contribution to this line of the work is the first algorithm that both achieves optimal expected stabilization time, log n, matching this lower bound, and does so using the minimal asymptotic number of states, which is log n, matching this lower bound here. So our algorithm consists of several small pieces. The main piece, the main novel component we contribute is this one. What it does is, given a junta, which is a set of agents of size between 1 and roughly square root of n, selects a set of polylogarithmic size quickly, that is in time log n. This is something that until now we didn't know how to achieve. And this is briefly how we achieve so. So simple observation is that if we start with a set of agents C that has a suitable polynomial size, we can quickly select a logarithmic subset, the C prime of this set. And one simple example of such a suitable size is, for example, square root of n, where this simple rule does the trick. Another such a convenient exponent, convenient size is n to the 3/4, which is the actual size that we use in our algorithm. So our goal now becomes that given a set J of size that can be anything between 1 and square root of n log n, we keep adding agents to this set until we obtain a superset C of size very close to this target size n to the 3/4. And this is the protocol that achieves that without requiring any knowledge of the size of J or N. So initially, all agents in J have value 1. All other agents have size 0. And these are the 4 rules. When a 0 interacts with 1, it becomes a 1, but only with probability 1/4. 1 and 1 create a new value 2. And then when a 0 interacts with a 2 or 3, then becomes a 3. So what we have essentially here is two epidemics that compete with each other, an epidemic of ones which starts with a larger support but is slower, and then the second epidemic that starts later but spreads faster. Okay, and then our set C is the final set of agents that are at state 1 or 2. This set stabilizes as soon as there are no agents in state 0, which happen after log n time. And the key technical lemma is that is to show that the size of C, of set C, is in fact very close to the desired, to the target size of n to the 3/4. And thank you.
Thank you very much. So we have time for a quick question or two while the next speaker sets up. So, I mean, I'm still waiting for questions, but could you already unshare your screen so the next speaker? Yes, thank you. So I don't see any questions. So thanks again. And we move on to the next talk. So the audio, yes, we can hear you now. And the next brief announcement is about intermediate value linearizability, and Arik is giving the talk.
Okay, so hi, I'm going to present a brief announcement on intermediate value linearizability, a new correctness criterion for quantitative objects is the full name of the paper. This is a joint work with myself and my supervisor, Edith Kedal from the Technion. So a motivating example is, for example, counting events, where we have servers A and server B. We have a controller, which is the laptop, and it needs to decide, do I need to start up another server because too many people are connected? And it knows that servers can handle 25 connections each. So if the total number of connections is 50 or greater, it needs to start up another server. So it asks server A how many people are connected to it. Server A replies 24. It asks server B how many people are connected to it. Server B replies 18. It sees that there are 42 people and there's no server needed. But this is all fine when things are happening sequentially, but what happens when things start happening concurrently? So for example, 6 people start connecting to server A, and the controller meanwhile asks server A how many people are connected to it. Well, server A hasn't updated its internal counter and therefore returns 24. The 6 people finish connecting and server B now has 10 people connecting to it. The controller then goes on to server B, trying to read how many people are connected to it. And server B finished handling these requests and therefore returns 28. So the controller sees 52 people are connected and thus needs to start up another server. If we analyze the time series of this short experiment, we can see that there's an increment in A, followed by an increment in B. Concurrent to this, there's a read, right? And the question is, what values can be returned by the read? Well, under linearizability, it's either 42 before both increments, 48 in between both increments, and 58 after both increments. But what's inherently wrong with the number 52? I know that at the end, I'll get to 58 and I'll need to start up another server. Well, what's wrong with reading 52 and starting up another server? Or what's wrong with any of the numbers between 42 and 58? I started at 42, so there I didn't need to start up another server. 48, I didn't need to start up another server. So what's wrong with the number 44? And this is the intuition behind IVL. We allow the return of any number between 42 and 58. Or to be exact, we allow any number to return that's between 2 legal linearizations. Right, so to conclude, we present IVL, which we find to be an intuitive correctness criterion. The values are bounded between legal ones, which means you couldn't work with this correctness criterion. And we show in the paper that it allows for sometimes inherently cheaper implementations than linearizability. And in the full paper that we'll present in DISC, we also define IVL for randomized objects and show a main theorem that shows that for a family of randomized objects which have bounded error, this is actually intuitively the correct criterion for these such objects. And in the example, we present sketches and a couple of other objects. So thank you, and I'll take questions.
Thank you very much. I don't see any questions yet, but if they show up in the next couple of seconds, we'll still happily take them. Thanks. The next speaker. There's a question by Andrea. So, no, it's not a question. It's just that it's hard to ask questions. So Mabo asks whether you do allow reductions.
So for the proposed batch counter in the paper, we don't allow reductions. It's an ongoing work trying to see whether we can provide an IVL counter which does allow reductions, or whether the cost of that is the same cost as a linearizable counter, showing that for reductions, there's no linearizable, there's no better way if you just choose IVL.
Okay, thank you. I don't see any further questions, so thanks again. And we'll move on to the next talk, which is given by Matthew, who we should be able to hear now.
All right, thank you.
Yes.
So go ahead.
Go ahead.
Okay.
You can read the title yourself.
My name is Matthew Rodriguez, and I'll be presenting work I did with my advisor, Michael Spear, on implementing software transactional memory in the C++ memory model. Now, the C++ memory model makes a decision that is inconvenient for those who wish to use sequence locks or implement STM or hybrid TM. It defines a data race as any concurrent access to the same data by two threads, except for when that variable is declared atomic. Now, it's natural for a programmer who wants to use sequence locks or implement a TM to believe it's okay for program data to be non-atomic. After all, it's protected by the sequence lock or by the transaction, right? Unfortunately, that's not the case. The memory model states that behavior in the event of a data race is undefined. Now, undefined doesn't mean, oh, well, maybe A happens before B or B happens before A, and when it comes time to commit the transaction, we'll figure out which one it was. No, undefined means there's no guarantees about how your program will behave. It means your program is not correct. Okay, you may say, well, the spec says this, but what about in the real world? Well, the impetus for this work was a bug we discovered in code we were doing for another research project, which was traced to this exact problem. We wrote code that was using sequence locks on non-atomic data, and G++ emitted code that didn't behave as expected. And the C++ memory model says that G++ is not wrong to have done that. So what did we do? We made the program data atomic, and it fixed the bug. So with that background, we've got two contributions. First, we note that some published STM and hybrid TM algorithms are incorrect, according to the C++ memory model. Fortunately, the fix is simple. We corrected all popular C++ algorithms for STM, which is about a dozen. In our evaluation, we measured the performance impact of the change on two ownership record-based STMs, one of which is eager or undo-based, the other one of which is lazy or redo-based. Fortunately, we found the impact to be very small. Now, C++ doesn't give a very good way of fixing the bug at the moment, but we were able to produce a working solution. For details on this or any other details, please consult the longer talk or the paper. Fortunately, the atomic ref construct coming in C++20 will give a cleaner solution to this problem. Our second contribution is as follows. The observation we made about the C++ memory model defining data races the way it does and the implications thereof has more severe implications for privatization, a common design pattern in some TMs. Privatization poses a known problem for TMs, and three strategies have been proposed to deal with the already known issues. First is quiescence, in which it's only possible to resume non-transactional code after all ongoing transactions commit. This works, but it's obviously a very costly solution. The second is an improvement on quiescence, in which the privatizing thread can resume non-transactional code a little bit earlier. Again, details are in the longer talk in the paper. And the third is the most ambitious, when it involves serializing all commits. Unfortunately, due to the way the C++ memory model is defined, strategy 3 cannot be correctly implemented in C++. Furthermore, while strategy 2 works fine for ownership record-based TMs, it does not work for ones which use value-based validation. In our evaluation, we measured the impact of switching back to simple quiescence on the no-rec-based STM, and we found that it was significant. However, there is currently no known working alternative in C++. Thank you.
Thank you very much. Again, we have time for questions. So do you think this is a problem which is unfixable in principle in the current version of C++ and the compilers, or could you imagine that a solution can be found, or is there any need for change in C++ itself?
As for the privatization one, I'm not sure. I think we believe it's currently impossible to implement the third strategy for privatization. I mean, the current solution is now to use the simple version of quiescence, which works, but is unfortunately the least scalable one. Changes would need to be made to C++ in order to support one of the more faster alternatives. We have a question from Edith in the chat. Was the full paper published? It was submitted as a BA. It was not. This was not like a full paper that was shortened to a brief announcement. This was. We did not feel the contribution was long enough to justify a full paper. Were there any other questions? Christoph, I think you're muted.
Oh, sorry. I have been talking all the time. It just had no effect. Thank you. So yeah, there are no further questions. Thank you for the talk, and let's move on to the next speaker. The next brief announcement is about self-stabilization in the face of high dynamics, and Anais will tell us more about what precisely that means. Please go ahead.
Can you hear me?
Yes.
Thank you. So this is a joint work with Karin Altizen, Stéphane Devim, Colette Jonen, and Franck Petit. We initiated some research about self-stabilization in highly dynamic networks. When I will speak about dynamic networks here, it means that the topology changes over time. So until now, self-stabilization mostly focused on static networks. In dynamic networks, one can use a self-stabilizing algorithm designed for arbitrary topology. And if you have let's say, the right assumptions on the topological changes, well, the system will recover after the topological changes, just as after a transient fault. So that's the argument that is sometimes used to say that a self-stabilizing algorithm is dedicated for dynamic networks. One can also use some variants of self-stabilization that are especially designed for dynamic networks, such as superstabilization or gradual stabilization. However, whatever solution you choose, this works only if you have few topological changes, if those are sparsely, so if those are, timely and geographically sparse. And it becomes completely ineffective when your topological changes are very frequent. So our question was, can we do self-stabilization in highly dynamic networks where the topological changes are not transient, but are intermittent, and where we cannot consider them as an anomaly, but when they are completely inherent to the system? And our first contribution is that we redefine the notion of self-stabilization in this highly dynamic context. We chose to model the dynamic of the topology using a time-varying graph. And then we focused on the fundamental problem of leader election. We considered 3 different classes of time-varying graphs. Those classes are defined according to the notion of connectivity over time. So one process can send a message to one another with a path that exists somewhere along the execution. All the edges may not exist at all time. And for example, class TCR is a class where every process can send a message to any other, but we don't have any time bound on how long it will take to reach the other process. And with these three TVG classes, we have both negative and positive results. So negative because we showed it is necessary to know the exact value of n, the number of processes, in two of those three classes in order to solve the leader election problem. But we have also positive results since we proposed three algorithms, one for each class. And it's a little too complicated to detail those classes, so I will invite you to watch the video and read our technical reports online to have more details on them. Thank you.
Thank you very much. So please post questions. In the meantime, just for clarification, so should this be read to mean that these two models are basically make very little sense because in such a highly dynamic setting, one wouldn't expect n to be stable? Or do you also see relevant applications or this model to be meaningful in this context?
Well, as long as the number of processes is fixed, actually, I think it can be used in quite practical contexts. We were actually quite surprised that we didn't need more bigger constraints. Here we do not need to have the network connected at any point of time. I mean, we do not need one point in time where the network is connected. It can be disconnected at any time. We just need some paths to exist. So in this way, it was quite surprising to need only this, but of course, we cannot use it if you have processes that enter and leave the system.
Okay, so I don't see any further questions. So thank you again.
Thank you.
And let's go on to the next brief announcement, which is going to be presented by Maget.
Thank you.
Yes, we can hear you. Great.
All right. Hi, everyone. So I'll present an algorithm extension to hazard pointers to protect immutable links to descendants of nodes. So a brief background is that hazard pointers allow threads to access objects, and concurrently these objects could be removed and reclaimed. But it does that by I'll go quickly through that. You have a thread here who's trying to access the object A. At the same time, another thread removed the object A, but then it doesn't reclaim it because it's protected. And then when the thread is done with the access, it clears the hazard pointers and it's reclaimed. So it's a safe reclamation mechanism. It has many advantages that that can make it sometimes the best option. The problem is that it has limitations on traversal of link structures. So for example, here we have a thread that's protecting object A, the node A. At the same, then concurrently some other thread removes nodes A and B. And since the thread is only protecting A, then B could actually be removed, reclaimed, and it's too late for our thread to actually do anything about protecting B and accessing. So we want to add extra requirements, and that's the algorithm I'm going to talk about briefly. And basically, I want to be able to unconditionally protect the descendants. So I want in our example to just unconditionally traverse to B with right now we have like hand over hand that using two hazard pointers that wouldn't give us that. And also I want to be able, if we remove like thousands of nodes and we have tens of thousands of hazard pointers, we don't need to go through them one by one. I want to be able to reclaim ancestors and descendants in the same pass on hazard pointers if they're not protected. So this is kind of very briefly outline of the algorithm. You can look at the algorithm in the paper, and it relies on these observations. If we use link counting, then of course we're gonna protect the descendants of nodes. Then we can, if we consider in general protection by hazard pointers, whether they exist or not, as one implicit collective reference, then that's another thing. And then we can combine these this one reference count with the number of links, and we combine them. And if we're dealing with immutable links, where links that can go, once they have non-null value, they cannot go, they cannot change. So if we apply that, this kind of guides our algorithm, then we can actually commutatively release these link counts or reference counts. So this allows us to achieve what the requirements I mentioned, and also it has zero computing cost for protection operations, which are the common ones, but then they add atomic operations to like release the link count and reference count. This is a very brief example that shows that we can actually go, reclaim any number of nodes in one pass if they're not protected. So here in our example, there's none of them protected. We have one thread, like one or more threads. They remove the nodes A, B, C, D, and then we do at some point, it's asynchronous. We go and say, okay, we want to see what we can reclaim. So we do a pass over hazard pointers. This is our one pass. There's no guarantee or requirement of what order we process the retired nodes. So let's say we're doing C, D, A, B. So that will go through them and reclaim them all in that one pass. So I just went through this kind of quicker than you can look at the longer presentation for that example. Finally, this evaluation on an x86 system, we can see that the traversal and protection is very fast. It's really very trivial overhead compared to let's say non-synchronized at all. But then we pay some price for determination of reclamation because we're doing this extra atomic operation to manage the counts. But we can see that this is like the fast part is actually the frequent and critical part, whereas the reclamation part is asynchronous and infrequent. It could be like hundreds, thousands, millions of times of protection compared to reclamation. Finally, this is, as I'm to wrap up, this is unconditional protection of immutable descendants. It allows same pass reclamation of ancestors and descendants. You can see that it's implemented and used in Facebook C++ library. You can find that code on GitHub, and thank you.
Thank you very much. There's a question from Edith. She would like to know if the solution doesn't work if there are links which are not immutable.
Yeah, no, it's there. So in the library we use like cases of link counting outside. So basically, we don't retire the descendant unless we reclaim the parent. I mean, the child and the parent. So it's kind of it goes. So if we have 1,000, so I use this in very short lists. Then yeah, that's okay. We're gonna like serialize that. We go multiple passes. But yeah, no, it's actually the immutability is helpful there, and I use it for these cases extremely like cheap. Yeah, but yeah, to answer that question.
Okay, thanks. So don't see any further question. Last chance. 3, 2, 1. Okay, so thanks again. So this brings this session to an end, and we'll continue in 15 minutes at 5:30 with the awards session and the business meeting. Thanks everyone again for the great talks, and also the participants for holding out until now. Okay, I'll hand over to you now, Jennifer. If I figure out how. There. You should be the host now. Huh, you're unmuted, but I can't hear you.
Can you hear me now?
Yes, that's better.
Okay, that was my fault. I had my microphone turned off. Okay, thank you.
Christoph, can you stop the recording?